This is the third part of the course by Dr. Igmar Saveri on the quantum physics. Please proceed. Dr. Igmar, let me start recording.
Okay. Okay, so let me try sharing my screen. Okay, so people can see everything okay?
Yes. Yes.
Great. Let's see. So welcome back, everybody. Where I'd like to start today, maybe I guess I'll remind people just a little bit of what we did at the end of last time. And then we'll dive a bit into p-adic versions of quantum mechanics. So the rough idea that we've sort of built up over time is that there are four options or roughly speaking, to sort of vary the structure of a physical theory. Let me just remind you of the way we numbered these. We had option 1, which was to vary the algebra of observables. And to do this without worrying about how the algebra of observables is built. So this we discussed a little bit, maybe in the second lecture it was. And this leads you to things like what's called arithmetic Chern-Simons or BF theory. You could also imagine varying the parameter space sigma and replace that by, for example, the p-adic numbers or a vector space over the p-adic numbers or some other local field. This is, I would argue, the largest class of p-adic models, and this includes things like p-adic QFT, but also p-adic string theory. And also sort of lattice models, what are called hierarchical models in the physics literature, which are closely related, in fact, to p-adic models. So this is, in a sense, a really big class. We could vary the nature of the degrees of freedom. And if we keep the notation from last time, we think about histories of the system as being maps from parameters sigma to some space x, then we could think about replacing x by some, for example, p-adic space, or replacing the mapping space. That's the thing we called E which was maybe a mapping space, but not necessarily. You could just consider the space E itself. And this is sort of where p-adic quantum mechanics belongs. There are other models of this type. People talk about, for example, p-adic classical mechanics, adelic mechanics. Lots of papers on ideas like this by Branko Dragovic, among other people, Volovic and Vladimirov, and several earlier papers. The last thing you could try to do is to vary the Hilbert space itself, or to change something in the way that you quantize the theory. So all of the above are really, in a sense, things that take place at the level of even the classical dynamics. Of course, p-adic quantum mechanics involves a quantum theory, but we haven't changed what it means to be a quantum theory. We've just changed sort of the nature of which time evolution or which observables we want to talk about, or how we parameterize the time evolution or something like that. The Hilbert space is still an object of the same sort. The last thing we could try to do is vary the Hilbert space structure. And last time we talked about some sort of fairly strong and, from my perspective, impressive no-go theorems that you can define in this context. Related to sort of ideas coming from quantum logic. By quantum logic, I mean the structure of various true and false propositions in quantum mechanics. And in quantum mechanics, a proposition that can be true or false is basically a closed subspace of the Hilbert space. So in a sense, I've said all that I really want to say about 4. And from my perspective, I guess these theorems are pretty strong evidence that, at least if we want to stick with the standard notion of quantum mechanical probability theory or quantum logic, there's not much room to change the structure of the Hilbert space. However, there's lots of room to change things in other places, and there are sort of strong structural results that indicate that that such changes are possible. In the way I'd like to think about it is that for 3, we need to ask about generalizing the canonical commutation relations, so studying the Heisenberg group. This is, I mean, it's the canonical commutation relations, but it's really the exponentiated. Canonical commutation relations. Over other fields or rings. And this, I mean, one way to think about this is that we want to, for example, understand how to quantize p-adic phase spaces. That's in 3, we've changed the nature of the space E, the space of degrees of freedom, or the space of classical states. And that means that E0, you'll recall that in the notation we had, E0 is our model for the on-shell degrees of freedom sitting inside of E. In classical mechanics, E0 is the phase space. And so the phase space is now going to be some kind of p-adic space, or a space that's defined maybe, at least in the linear case, as a vector space over some other local field. And we need to understand what it means to quantize such an object. Sorry, not 4, but 2. We need, I guess, many things, but above all, p-adic analogs of Fourier theory. Related to the mode decomposition of a field. As well as integration. And if you sort of think about, for those of you who have seen maybe a more traditional quantum field theory course, the typical thing that one does in a quantum field theory course is one studies, for example, like a bosonic field. It has some equation of motion that it satisfies. And one finds that one can decompose into eigenstates, not eigenstates, but eigenfunctions of momentum. So translation invariant field configurations, or translation covariant field configurations, which look like plane waves. And then to quantize the theory, one just notices that the dynamics are effectively those of a collection of harmonic oscillators, one for each momentum mode. And one introduces creation and annihilation operators, in other words, a copy of the canonical commutation relations for each momentum mode. And so the distinction between option 3 and option 2 is going to be, are the canonical commutation relations the standard canonical commutation relations? It's a normal set of very many harmonic oscillators, but labeled by, for example, p-adic momentum modes. That's option 2, where the parameter space is p-adic. In option 3, we really need to think a bit about what a p-adic version of the canonical commutation relations themselves, what a p-adic version of a degree of freedom should be. So I'm going to work backwards. I think this time we'll talk mostly, so in the next hour, about option 3. And then we'll come to issues related to option 2 and models related to option 2. So to discuss 3, we're going to talk a little bit about the general theory of the Heisenberg group. This is sort of an abstract way of formulating what it means to be able to canonically quantize something. So let's imagine that we have a phase space, which is just a symplectic vector space. And I'm going to take the simplest possible example, which is really just a vector space V. With an antisymmetric pairing. And in the normal case, that pairing would be valued in R, the ground field. But here I'm just going to let it be valued in the ground field of the vector space V, some field K. And V could be a vector space over K, where I don't need to know any properties of K. So K is any field. In fact, it could even later be a commutative ring, but let me come back to that. I'll just make the remark here. It's sort of very, very general construction. V is, if you like, an additive abelian group. Like, you can think of it in two ways. You can think of it either as an abelian Lie algebra, so generating translations, representing infinitesimal translations, either of the momentum or of the position. Or you can actually think about exponentiating it and considering finite translations. And the Lie algebra of the additive abelian group V is, again, just isomorphic to V as an abelian Lie algebra. So there's a central extension defined by this pairing omega, which takes the following form. If I'm thinking about groups, it's really going to be K thought of as the additive group. And then I'll call this the Heisenberg group associated to V omega. There's a quotient which is V. That maps to 1. So this is a short exact sequence of groups. K is abelian. It's actually central in the Heisenberg group. It commutes with everything. V itself, as a quotient, is abelian, but there's going to be an extra group operation defined by the cocycle, which is omega. So it's maybe easiest to see that omega defines a Lie algebra cocycle. It's an element of the second symmetric, second exterior power of V dual, which is just H2 of the Lie algebra, if you're familiar with Lie algebra cohomology. But that, I mean, that's an unnecessarily fancy way of saying it.
Sorry, but
yeah,
a question about the notation. In the exact sequence in the last line, V is the additive group corresponding to the vector space V, or is in general additive abelian group?
It's the additive abelian group of the vector space V.
Okay.
So it's important that this is isomorphic to K to the N, viewed as an additive group.
Thank you. Thank you.
Other questions at this point? So let me do an example, which is
excuse me, Ingmar, just one question.
yes.
Should it not be 0 at the end of that short exact sequence, since V is an additive group?
Right. So if we're writing it additively, we should write 0. That's right.
I thought mostly on the right-hand side. Yeah. Okay. Yeah.
Yeah.
Okay. Thank you.
Yeah. So I mean the trivial abelian group, but I guess if it's depending whether it's multiplicative or additive, it could be called 0 or 1.
Okay. Thank you.
Yeah. It's since we're working additively, it should be 0. Thanks. So the central extension is going to be defined for any such data, but it's easiest to think about the data where V is just two copies. It's a two-dimensional vector space over K. And then we can actually represent this using 3x3 matrices. If V is K squared and omega of AB, A prime, B prime is just the standard antisymmetric form, which will look like AB prime minus A prime B. You can think of this as being, of course, you should imagine, right, that V is a phase space, and this symplectic form is really just the constant coefficient object dp wedge dx. And we're just writing it out in coordinates here. We can consider the subgroup of 3x3 matrices, which are strictly upper triangular. And I claim that the Heisenberg group is actually isomorphic to the set of matrices of the form P, Q, C, and zeros below the diagonal. And I want to view that as a subgroup. Of course, these are all invertible, so it's really a subgroup of the invertible 3x3 matrices over K. Now, if we think about how things compose here, we need to multiply two objects of this form. And you notice that I just recover the additive group structure on the P's here. Here I get just Q plus Q prime. Here I get nothing but this, so I land back in the collection of strictly upper triangular matrices. But something interesting happens on the very last entry. Namely, I get C plus C prime plus PQ prime. So the group law is slightly different than you might expect. And this is a thing you may recognize from the exponentiated form of the canonical commutation relations. So I can think of the elements of this form, Q, as generating finite translations. Generating is wrong. I really mean consisting of. So these are the finite translations. Now you might ask, it's all very well to work with this group of finite transformations, but why didn't I work with the generators? It would have been more convenient to just write down the Lie algebra. the Lie algebra, it's easy to do. If I take derivatives with respect to P, Q, and C, I'll see that the Lie algebra consists of strictly upper triangular matrices, no ones on the diagonal now. And those strictly upper triangular matrices, they have a Lie bracket, which is just given by the commutator. And then in fact, it's obvious that the Lie bracket reproduces this form omega. Well, the advantage of writing it in this way is that because things are already exponentiated, I don't have to worry about whether or not it makes sense to think of the Heisenberg group as a continuous group. In particular, I didn't have to say anything about the topology on V. I don't have to know that V has a well-behaved tangent space. If I define the Lie algebra, I often need to think about, well, taking derivatives or looking at vector fields. I don't need to do any of these things to construct this group. It in fact just makes sense no matter where P, Q, and C take values. So there's no problem defining this group. For example, over a finite field, it'll be some interesting group. There's also no problem defining it over the integers. The integers are not a field, but I could consider matrices with integer entries of this form. And I would find that they're all invertible and they form a non-abelian group, which is the analog of the canonical commutation relations. The exponentiated canonical commutation relations. So how do I go from here to quantization? Well, the idea is that I'd like to think about, I've sort of, in a sense, done something sly by writing it in this form. Namely, I've chosen to privilege symmetries over observables. So there's going to be, in the normal case, yet another one of these results that connects symmetries and observables, which just says that given a Hermitian matrix, so an observable, I could imagine exponentiating it and constructing an element of a one-parameter Lie group. And that would be a one-parameter group of unitary transformations on the Hilbert space. So some kind of symmetry. And correspondingly, if I have a one-parameter unitary group acting on the Hilbert space, I could take the derivative with respect to the time parameter, and I could pull out some Hermitian generator, which is then observable. So in the normal case, these correspond. But in general, this might be tricky. Precisely because the correspondence between Lie algebras and Lie groups sort of uses facts about the topology of the real numbers in an interesting way. But it's fine to pick one, for example, the action of finite symmetry transformations, and ask how much of the story works there. And this is more or less what one does in p-adic quantum mechanics. So the key fact now is going to be that given this group of symmetry transformations, which is generated by the canonical commutation relations, that clearly acts on the Hilbert space. In fact, when we construct the Hilbert space, we want to do it so that the canonical commutation relations are represented on it. But you'll notice that we never talk about a choice of Hilbert space in quantum mechanics. So you might ask, why is it the Hilbert space? And not a choice of representative of the canonical commutation relations? Representation, sorry. And the answer is that there's a theorem by Stone and von Neumann which says that the real Heisenberg group has precisely one irreducible unitary representation. For each non-trivial central character. What do I mean by central character? Well, if a group has a center, and in fact, the Heisenberg group does have a center because it's a central extension, then that center is represented irreducibly because it commutes with everything. And if the representation is irreducible, then the center acts everywhere, and I can go between the vector space by acting with different elements. So that means that any irreducible representation is characterized by a single irreducible representation of the center. Those are all one-dimensional because it's abelian. And so they're all characters. The central character just means the choice of irreducible representation of the center. And what that really means in this context is the numerical value of h bar. So normally we think about h bar as being a parameter. It controls sort of the strength of this central extension. You can see that because we say the commutator between x hat and p hat is proportional to h bar. In a sense, you can think of that as being a property of the representation. And there exists exactly one representation for every choice of the value of h bar. But it's sometimes convenient to think about h bar as being a formal parameter which takes on a value when it acts in the Hilbert space. That's kind of the trick that's being played here. And so this means it's totally fine to think about the Hilbert space. It's unambiguous what I mean, because I mean the unique, up to isomorphism, unitary irreducible representation of the canonical commutation relations. And in a sense, this is the reason why all of these pictures, the Heisenberg and the Schrödinger picture, and the position momentum and the the position representation and the momentum representation, why all of these things end up being the same and representing the same physics, it's because there's sort of one object, and that object is already uniquely specified by the form of the Poisson bracket of the classical observables, which is kind of, again, remarkable. So now there are lots of generalizations of this. So in fact, the structure of the Heisenberg group is such that its representation theory works pretty well over any commutative ring. So for example, if I take K to be Fp, the representation is on functions from Fp to C. And the representation acts by saying that, oh, I didn't name these generators, did I? I think I should name these generators something like UQ, VP. So one of these is going to act by translations. The other is going to act by translating in momentum space, which is multiplying by a character. So I'm in sort of implicitly the position representation here. The characters of Fp just look like pth roots of unity, the additive characters. Oh, the notation is kind of terrible now, isn't it? I have two P's. I think I need to change the name of the momentum to something like K. Oh, I already have a K though. Hopefully it's fine if the momentum is called S. So I'm going to try to adhere to the following convention. K is a field. P is a prime. Q is a coordinate. S is a momentum. Sorry, that's a bit it's a bit unfortunate. So we can just think about how the canonical commutation relations are represented here. It's going to be familiar to you because it's exactly the way they're represented in every case. Question?
Yeah. So it seems that you forgot something in the representation of Heisenberg group. You just the character. Oh.
Yeah, there's definitely a phi there. Is that that was what was missing? I hope.
Yes.
Yeah. Okay, so if I do first v and then u, then I should take the shift of the expression, which is phi multiplied by a character. So it should look like the 2 pi a minus q s over p, phi of a minus q. Whereas if I do it the other way, it should look like first shifting phi and then multiplying by a character. So it'll look like so that means that the canonical commutation relations are valid in the form UQ VS. QS over P VSCQ. And those are precisely, this is the sort of exponentiated form of the canonical commutation relations. So people have seen these before. These are, in this case, just finite matrices, because phi is a function from a finite set to the complex numbers. So these are the so-called clock and shift matrices. UQ will look like this. And VQ will just consist of the pth roots of unity in order down the diagonal. That's just the matrix representation of these formulas here. But I want to emphasize that nothing in these formulas depended on where these symbols took values. The only thing that's important is that I know how to multiply them, and I have some notion of an additive character. So of course, the same formulas apply to Z, R, QP, and so on and so forth. Now you might ask, the following question. Before we constructed the real canonical, so the real Heisenberg group, using 3x3 matrices. So why isn't there a three-dimensional representation? In fact, a three-dimensional real representation. This group? And the answer is there is. But it's not unitary. In fact, you'll notice that none of we wrote down, in fact, upper triangular matrices. None of them are going to be diagonalizable. They're all going to look like they contain Jordan blocks of various different sizes. And in fact, that's necessary. As soon as one of these matrices is diagonalizable, then the arguments that allow you to prove the Stern von Neumann theorem apply. effectively, those arguments proceed by taking an eigenvector with an appropriate eigenvalue, and then acting, showing that the, for example, if I have an eigenvector of v, then the action of u shifts that eigenvalue. And that sort of means that the representation has to be at least as big as functions on the space of possible eigenvalues. In fact, that's how big the Hilbert space always is. Operators in Hilbert space, the spectrum is the real line. We end up with complex valued functions on the real line. So on and so forth. There will be numerous, it's probably in fact not even understood how many different smaller real representations there are. The important thing is that none of them are unitary, and so they don't work well to define quantum mechanics. Okay. So we have, in particular, the p-adic frictions. The canonical commutation relations. We can just write, again, operators UQ and VS, where Q and S are p-adic numbers. And these will satisfy the commutation relations QVS equals chi of QS, VS, UQ. Perhaps I need a negative sign in the convention that I have up there, but I think there's a convention that makes this work. And this is represented on L2 of QP. Again, by totally analogous formulas. So one of them will act by a shift, the other one will act by multiplication by a character. But you might ask, how should we introduce dynamics? In particular, it's not obvious. So of course, we could say, again, observables are Hermitian matrices that act in the Hilbert space L2 of QP. That Hilbert space is the same as every other Hilbert space. We know what it means to be Hermitian. But we don't necessarily have a good correspondence between observables and symmetries. And so in particular, even if we define the Hamiltonian as an observable, we don't know how to use it to generate the one parameter flow, which is time translation. That's slightly more complicated. So the idea that one uses in p-adic quantum mechanics is, roughly speaking, the following. In classical mechanics, in other words, on the phase space, there are ways of understanding. Time evolution as canonical transformations. What that means is that the Hamiltonian will classically generate a flow that flow will act on the phase space by a transformation that preserves the symplectic structure. And in particular, for free, by which I mean quadratic dynamics. So. We just need to understand linear canonical transformations. Of the phase space V omega. So people will have seen this, I'm sure, in the normal formulation of the harmonic oscillator. So, example. The harmonic oscillator has coordinates, I guess I'm now calling them Q and S rather than Q and P, but it's one position and one momentum. And the Hamiltonian is something like 1/2 Q squared plus S squared. And this generates a flow. In particular, there's a vector field defined by omega of x h with whatever being the derivative. And the derivative is q dq plus s ds. That's the one form, which is the exterior derivative of the Hamiltonian. And if we solve for what xh looks like, you'll remember that omega is ds dq. So that means that this Hamiltonian vector field, to get a dq, I need a dds. To get a ds, I get a dq. And if I draw what that vector field does, that's the vector field that generates uniform rotations of the phase space. And you'll recognize that, in fact, those are the trajectories of the system. What happens to a state in the phase space is that it orbits around in a circle of fixed radius because the Hamiltonian is conserved. So that means that finite time evolution is just given by specific matrices, which are just literally rotation matrices. And that's a one parameter subgroup of the symplectic group. Now, in the p-adic case, we don't really understand, or at least I don't have a clear way of saying why this part of the story makes sense. We can't really translate very cleanly between observables and flows at the quantum mechanical level. But we certainly understand what automorphisms of the phase space are. In particular, we have a good analog of canonical transformations. Namely the symplectic group of V omega, where V, this could now be, for example, an integer symplectic group. It could be a p-adic symplectic group. It could be whatever. It's just the group of k linear transformations that preserve the form omega. And Stone von Neumann gives us something even better. So for example, it's not obvious when we construct the Hilbert space using the position representation. The symplectic group will act and it will shift position into momentum, and it will not preserve that choice of polarization. But Stone von Neumann means that we'll always be able to construct a representation with respect to our new polarization, which is isomorphic to the one we started with. So that means that there's actually going to be an action of the symplectic group on the Hilbert space up to a phase. So we don't know, for example, that we can, given a symplectic transformation, get a unique self-map of the Hilbert space, but we can get a self-map up to a scale, up to a non-zero complex number. And in fact, if you work a little bit harder, what you find is that you can construct a projective representation of canonical transformations on the Hilbert space. And in fact, this is 2 to 1, usually. So the main idea in many versions.
Sorry, time for the break.
Yeah, so I'll just say, I guess, one sentence to wrap up, and then we can take a half hour. I think all I want to say here is that in many versions of p-adic quantum mechanics, the way that dynamics are constructed is just by constructing appropriate subgroups of the canonical transformations, so in a sense working classically, and then quantizing by letting those subgroups act on the Hilbert space in the way that we just described. So rather than solving a differential equation that shows you how the quantum dynamics behave, you sort of construct the group of all time evolutions just as a subgroup of the p-adic group of symplectic transformations of the phase space, and it's represented naturally by matrices. And that's in a sense the quantization of that p-adic time evolution. So let me leave it at that and ask if there are questions.
Are there questions or comments? No, for the moment.
Great, okay. So we'll resume, it's at 6 o'clock, right? So you're 11 a.m.? Great. Thanks, everybody.
Yes. We have a break, 30-minute break.
We'll send 10 minutes or until 11? Yeah.
Are you saying something?
I was just curious when we start again. 11 o'clock?
11 a.m. local time in Mexico.
Perfect. Okay. So we'll see you.
You have just 30 minutes.
It looks like 25 to me, right?
Yeah.
We'll see you soon.
Okay, thanks.
Pero es a las 11 que regresamos.
Okay, let us resume the conference. Please, Igmar, proceed.
Okay, so maybe let me just say another quick couple of words to make slightly more concrete what we were saying about p-adic quantum mechanics. So the idea for studying time evolution.
We are not seeing your screen.
Sorry, yeah. Thanks. Let me share again. Now you should see it?
Yes.
Great, okay. So the idea for studying time evolution was roughly to look at the corresponding subgroup of the symplectic group excuse me, and then to let this act on the Hilbert space. Via the projective representation there. So just to maybe quickly demonstrate that this is something concrete that you can do. This is stuff that's familiar from the old p-adic quantum mechanics literature, but I don't know. It's, I think, worth discussing. For example, we could think about the free particle. So the trajectories of the free particle look like this. They're just lines of slope p. And so that means that the time evolution subgroup is by the matrices of the form 1T01 inside of SP2. Okay. And if I wanted to quantize this, that means that I would try to find unitary operators m sub t, such that conjugating by m sub t transforms the observable x into the observable x of t. So that means in equations that I should impose equations like m sub t This is saying that the momentum doesn't evolve in time. So that's sort of the bottom half of this matrix. Sorry, this is like this. And these are, roughly speaking, just the quantizations of the things we would have solved for above. So one of these is saying that a state with momentum p, if you evolve it in time, also is translated in space by an amount pt. Whereas a state that's shifted in position and then evolved in time, this is saying that
a question about the notation. In the last equation, P stands for position, not for a prime number.
Sorry, this is the thing that I should have done above. So these P's are S's.
I think that you use S, perfect S before. Perfect.
Yeah, so to remind myself, S is momentum. Q is position. Sorry about that. Right, so in a sense, what this equation is saying is that spatial translation and time translation commute. That makes sense, right? So if I take a particle which is moving with a constant speed, I let it evolve in time, and then I shift it 5 meters to the right. I could have shifted it 5 meters to the right and let it evolve in time. It would have had the same effect. Whereas the second equation is saying that if I have a particle that is being shifted in momentum, if I shift the momentum by s, evolve in time, and then shift the momentum back, the particle ends up translated in space compared to where it would have been had I evolved in time without translating the momentum. And sorry, there's an ST here. Now this looks correct. This is like the commutator of momentum shifts and time translations. Is a spatial translation. And I want to emphasize that, so the way things are written now, I could be doing just the quantum mechanics of a real free particle. It would work exactly the same way. The point is that I've set it up in such a way that it functions over the p-adx2. There's no reason to take S and T to belong to any particular field. So now I can compute matrix elements. Of the time evolution operator, if I want to. For example, if we wanted to compute something like this matrix element here, Well, y is just the translate by an amount y in the spatial direction of the state 0. But I know that spatial translations commute with MT. That's my first equation up there. And then I could also absorb the x into a shift here. I could derive an equation of this form. Now, if I wanted to use the second equation, I'd have to choose s to be x minus y over t. You'll notice that I've set h bar to 1 and I've set the mass to 1. So I'm ignoring a lot of parameters here, but that's fine. Then the equation above would say, the second equation, let's just read it. Be x minus y over t, mt equals mt.
Excuse me,
Yeah,
there is a question.
please.
Okay. Do you want to ask something? Go ahead.
Yeah, I don't understand that the shadow of
There is a question about the Dirac notation.
About the Dirac notation.
Yes, just because some of the people in the audience are not physicists, so they are not familiar with the Dirac notation.
Great, okay. Yeah, so this notation, what this notation refers to is, this is, I guess, fairly common in the physics literature. So I'll make a side note about this. So we've written all of these objects U, V, M, and so on are unitary operators on a Hilbert space. And that Hilbert space I can think of as being L2 of K, where K is, for example, the p-adits or whatever field is being used right at the moment. It's L2 with complex coefficients. So often what we do is we write X. Implicitly, what this means is there's sort of an improper element. X0 is delta of X minus X0 in L2 of K. So it means the element of this Hilbert space, which is an eigenfunction of the position operator with eigenvalue X0. And when we write it this way, this is the dual element to X0. And so in particular, a notation like this, it really means that we're taking the inner product in the Hilbert space between the state 0 what's the best way to write it? So, I mean, I guess the best way to write it is that a notation like this means the inner product of the eigenvectors with eigenvalues A and B. And of course, it's implicitly referring to some operator, the eigenvectors of some particular Hermitian operator with those eigenvalues. And in this case, that operator is the position. It's of course slightly it's of course not exactly correct to say that the delta function is an element of the Hilbert space, right? In the same way that plane waves are not elements of the Hilbert space. So what we sort of really mean when we talk about these things is the limit of some set of regularized things that approximates those. Is that okay?
Yeah, but why do you have figure to be defined like something we have to?
Hi.
Hi.
Yes, the part with two objects is understood, but what does it mean when you have three in that case?
Well, so MT acting on X is just an operator acting on the vector X, right? So this is some other vector, and I can act with two operators successively. So you can think of this as being like the product of two matrices, for example, or two, I mean, they're really two operators in Hilbert space, but they have a well-defined product coming from acting with one after the other one.
Perfect. Thank you.
Thanks very much. Other questions at this point?
No, not for the moment.
Great, okay. Let's see. Let me move this down here. So what I'm doing is I'm taking this commutation relation here. I'm choosing a specific value for S, namely x minus y over t. And what I'm finding is that Vx minus y over t times mt equals mt, and then there's going to be a number here, which is the additive character minus 1/2 x minus y squared over t. And there's going to be ux minus y. And then Vx minus y over t. So that means that the object I want to replace, let's see, the object that appears in that matrix element is this. So I can rewrite that in the form mt ux minus y equals Vx minus y over t, mt Vy minus x over t. I've multiplied on the right, and then I have the number chi of and if I look back at this matrix element here, I can now replace the operator by this other expression. And because this is the eigenstate with position 0, these V's are going to act on that trivially. They're going to act on that just by 1. So what I've found is that x mt y is proportional to 0 mt 0. This is just some number times the additive character of the field evaluated at 1/2 of x minus y squared over t. And this is in fact the classical action of a trajectory, joining x to y. So if you were to remember that there's a straight line path that joins x to y, and you were to integrate the classical action, you would find precisely that quantity. And so you should think of this as an analog of the path integral formula. That says that the expectation value, if there's a well-defined path integral from propagating from x to y in a time t, this is proportional to some universal constant times the exponential of minus the classical action for the trajectory that joins x to y. So this is in a sense the way the story would go in p-adic quantum mechanics, and you can generalize this to other quantum mechanical systems, things like the simple harmonic oscillator and so on. But the flavor is kind of similar. Namely, you see some sort of very familiar formulas, or you see very familiar objects appearing. You see sort of an intuition being validated, which is that the classical action of a trajectory becomes proportional to the matrix element in quantum mechanics. This was an ansatz of, I think, Freund and Olsen. In the p-adic case. But the time evolution now is something quite abstract, and I want to emphasize this. We don't have, for example, a real one-parameter subgroup of the group of p-adic canonical transformations. We have, in a sense, a p-adic one-parameter subgroup. It's controlled by a p-adic time parameter, namely this t, which is floating around. And what we've got is a map of groups from the additive p-adic line, which you think of as time, that maps into unitary transformations of L2 of QP. So we get a unitary, again, complex unitary representation of p-adic time translations. And so in that sense, there are issues with ordering. Or you might ask questions. And this was the question that Wilson was asking yesterday, I believe. Things that have to do with the total order on the time, such as, for example, causality. Those are going to be a bit subtle in this scenario because, of course, the time is now represented by a p-adic variable, but that p-adic line is not totally ordered. And as such, there's no real way to totally order events, even in the case of just a quantum mechanical system. Okay, that's maybe all I wanted to say
ignorant.
Yeah.
It seems that in this framework, we don't have a Schrodinger equation.
Correct. Correct. So in a sense, the Schrodinger equation would say, something about the fact that the infinitesimal generator of time translations is the observable, which is the Hamiltonian.
Yes.
And sort of because at the quantum level here, we don't know how to go back and forth between finite transformations and observables, we can't really say that, we can say that this is a family of transformations, which represents time translation that has one p-adic parameter. And it's a homomorphism of groups from the additive p-adic numbers to the unitary group. In a sense, it's hard to say what the Hamiltonian should be. It is as though we know what e to the iht is, but we can't define h. I think that's the way I tend to think about this formalism. And it comes down to the fact that there's no really great analog of at least to the best of my knowledge, there's no really good analog of the correspondence between observables and symmetries, or observables and flows.
Mathematically speaking, the main obstruction is that we don't have a theory for semi-group with chaotic time.
Yeah, I think that's the way you can say it. You have here like a representation of the additive group QP, which is by unitary matrices, but you don't know how to say that that subgroup of the unitary matrices is generated by a single Hermitian matrix.
Exactly.
Yeah.
Thank you.
Yeah, thank you. That's a good question. So that's mostly what I had to say about p-adic quantum mechanics. So maybe it's a good place to see if there are other questions before I move on. And once I move on, then I'll talk more about these models of class 2. So models where the parameters are p-adic, but the degrees of freedom are real.
We don't have additional questions at the moment.
Great, okay. So let's move on in that case to models of class 2. So here the dynamical degrees of freedom are all real. It's the parameters that are, in a sense, p-adic. So, as I was mentioning before, it's sort of the theory of special functions, or it's Fourier theory on the p-adics that really plays the essential role here. That's what lets you think, for example, about momentum modes or plane wave solutions. Those are roughly just given by the basis of additive characters. So something which I always like to remind people of is that there sort of the hallmark of models of this type, or a large class of models of this type, is sort of a family of universality results. And what that means is that there will be field theories which I can define in exactly the same way on real and p-adic spacetimes. So let's say that those spacetimes are vector spaces. Over any local field. And then the results of computations. So these are things like anomalous dimensions, correlators, or whatever, are actually independent of place. What I mean by independent is not that the number that you get is independent. The number that you get is quite different, but that number is always constructed in terms of special functions. And when you express those special functions appropriately for each place, for each local field, then the result is takes a universal form in terms of the appropriate special functions for each place. And those special functions depend on the place because they're built from, for example, additive and multiplicative characters, integrals with respect to the additive or multiplicative Haar measure, and objects like that. So when expressed in terms of special functions appropriate to each place. So this is perhaps a little bit abstract sounding. It's always good to do a concrete example. So for example, to construct the zeta function, we should sort of follow the following recipe. Let K be any local field. Because it's a local field, it's Fourier self-dual, meaning that the Fourier transform maps square integrable functions on K into themselves. So let's let theta be the fixed point of the Fourier transform. In fact, I claim that I'll always be able to find a function which is fixed, which is its own Fourier transform. And let's let chi be a multiplicative character. And d star x multiplicative Haar measure. then the claim is that we should define the zeta function appropriate to k to be the integral with respect to multiplicative power measure of the multiplicative character times the fixed point of the Fourier transform. And so the zeta function is really a function of the multiplicative character. Normally we think of it as being a function of a complex variable, and we do that by taking pi to be the norm on the local field to the power of some variable s. That gives us zeta k, depending on a variable s. But you can consider other multiplicative characters too. And this is sort of work. This is the way Tate thought about defining these functions in his thesis, I guess, which is a sort of a cornerstone of analytic number theory, maybe. So let's see what we get. Well, if k is the real numbers, then theta is going to be e to the minus pi x squared. And so the object we're sort of trying to compute is zeta r of s, which is the integral over r dx over the norm times norm to the s, that's pi, times e to the minus pi x squared. Well, that's twice the integral over the positive real numbers. X to the s minus 1, e to the minus pi x squared. We can substitute and let u be pi x squared. And then du is, I guess, 2 pi x dx. So that means that we'll get the integral over r plus du u to the s minus 2 over 2, e to the minus u, and then there's a factor pi to the minus s over 2 coming from this change of variables. And if we remember the definition of the gamma function, this is pi to the minus s over 2 times the Euler gamma function of s over 2. So, now for those of you who've seen the zeta function before, the global zeta function, you may remember that the zeta function is normally the product of a bunch of local factors over all of the primes. And then it satisfies a functional equation. And that functional equation looks a little bit strange because it involves some extra factors of pi and also the Euler gamma function. So it turns out that if we do the same over the p-adics, let's just go ahead and do this computation. We're going to integrate over qp. The Haar measure is again dx over x. We've got a character of the form x to the s minus 1. Now the object, which is Fourier self-dual, is the characteristic function of the p-adic integers. So we can take care of that by just integrating over zp instead of qp. And in fact, I need to introduce a normalization factor here, such that the unit circle has volume 1. That factor is going to look something like p over p minus 1. Well, I can compute this integral easily, right? It's just a sum. So I sum over the the valuation of the p-adic integers, I've got p to the minus sorry, this minus 1 is silly here. Let's see. Go through this carefully. So I've got, first of all, the size of the circle of radius nu. That's p to the minus nu. Then I've got 1 over the p-adic norm. That's p to the plus nu, because the norm is p to the minus nu. Then I've got this term here, which is the norm to the power of s. That's p to the minus nu s. Then I've got the size of the unit circle, which cancels this factor here. So at the end of the day, this is just the sum of p to the minus nu s, which is 1 over 1 minus p to the minus s. And you'll notice that that's indeed the local factor of the Riemann zeta function. That's defined to be the product over primes of these local factors. If we include the contribution at infinity, so we get a sort of a completed version. Maybe I'll call it z of s with a simple functional equation. It'll just look like that. And so what this computation is meant to emphasize is that if I think a bit abstractly about what the zeta function should do, and I define it in terms of objects that make sense for any local field, the fixed point of the Fourier transform, the multiplicative Haar measure, and some multiplicative characters, then I'll have a concrete way of defining the zeta function for any local field, as we've done here. If I have a global field, I can multiply over all of its places, and that object is going to, in a sense, have the nicest properties. So this way of defining the local factors of the zeta function, in fact, gives me precisely the correction term, this sort of strange-looking correction term that I need to get the functional equation correct. And that's, in a sense, hinting at an adelic origin for this functional equation. So let's write down a couple examples of typical p-adic field theories. Well, I'm going to have fields which are functions from something like qp to the n to x, where x is, for example, R. That would be the theory of a p-adic scalar field. So let me write it in this way. I'm going to think about one scalar field on qp to the n, So this is a field theory in n dimensions in a p-adic space-time. It's a theory of one real scalar field. We sort of need to construct kinetic terms. But this is not that hard to do because we already know what the analogs of waves are. The analog of a wave is just going to be built from an additive character of the p-adic field. So what this notation should mean is that x is a coordinate on QPN. K is dual to that coordinate. And so k dot x is an element of QP coming from evaluating a covector on a vector. And k right now is arbitrary. It's just sort of like a wave number that I chose for this wave. And this is the analog of the formula e to the, sorry, 2 pi I k dot x in the real case. So it really is telling me about some kind of plane wave. And that should be a wave of momentum k. But of course, we don't really want the momentum when we think about, for example, constructing an action functional that weights plane waves by their energy. In the real case, we use sort of the norm of the wave vector. We use k squared. So in this case, one logical guess is that you might want to assign an energy. Proportional to a power of the p-adic norm of k. And so, for example, in momentum space, a good free action functional is just defined by taking it to be diagonal in the Fourier basis. So it'll look like this. So phi looks like integral dk1 integral dk2. We've got a delta function that enforces momentum conservation. Then we've got the product of our two fields in the momentum basis. And then we've got a weighting factor proportional to the square of that momentum, something like this. So I want to emphasize that what this is saying from a physical perspective is that plane waves, the space of p-adic fields decomposes by Fourier theory into sum over plane waves. And those plane waves don't interact with one another at all. So they're, in the free theory, there's nothing that can change the momentum. The only thing that one does is that one writes down an action functional which is quadratic, and where the coefficient of that action functional is proportional to the momentum of the mode it's sitting at. So this is in a sense analogous to what you would do when you would say each momentum mode of a field in a normal field theory can be thought of as an uncoupled harmonic oscillator, where the excitations of that harmonic oscillator are the quanta of the field. You think of them as particles with energy, p squared plus m squared. And the fact that the frequency depends on the momentum is saying that creating one particle in a given mode, creating one quantum in a given mode, costs more energy if that's a high energy mode with a lot of kinetic energy, short wavelength, than it does if those particles are at rest. So in a sense, precisely the same thing is happening here.
Ismael,
Yeah.
a comment about the action. The action can be written in a simplest way as the Fourier transform of the field, the norm of the Fourier transform of the field times the factor that you have.
Mm-hmm. So you're saying if I take the delta function out, then I
Yes, exactly, because this is more complicated. It's just the Fourier, it's just one k, the k, the Fourier form. Okay,
yeah.
yes, yes,
Like
and then the factor, yes, the energy factor.
Yeah. Exactly. So in fact, the only reason I put these both in is to emphasize that when we write higher order terms, there's always going to be more than one integral, right? So for a term of order phi to the n in momentum space, there's going to be sort of n minus 1 independent integrals. Because roughly speaking, there will be n Fourier transforms, so n different integrals, and one delta function that conserves momentum. So maybe just a quick question about the schedule. I guess the conference will start right at, let's see, what time would it be? Immediately after this, right? So should I plan to end at my 8 p.m., your 1 p.m., or slightly before, or?
You have 2 hours, let me see. You are supposed to end at 1 p.m.
1 p.m., okay.
Local time.
Great. So maybe it's a reasonable time to take a short break in the middle, and then we can resume in, say, 10 minutes, 5 after, and then I'll go until 1.
Perfect. Thank you, Ima.
Great. Thank you so much.
Es que lo escribió así porque mete la conservación del momento. Pero cuando usted ya se el y ya cada uno es igual a cada dos. Pero miren, está realmente la transformar y es de la fin con claro. Haz que los hechos no. En la normal para sacar los escribir. Sí, no lo usan. Porque ya están en momentos están muy pesado. Claro, las cosas ahí. La notación, por ejemplo, de estas cosas. Realmente, cuando describió la segunda forma, es así como sí, pero la otra no. Are you ready?
Yeah, I think I'm ready to go. Great. So welcome back, everyone. So what we're getting to just at the end of the last hour was a little bit of discussion of how one might construct free field theories over a vector space, so living on a space-time which is a vector space over the p-adic numbers. And the point was that, roughly speaking, we could do this in such a way that it mirrors the normal intuition that the action functional is diagonalized in momentum space. If we have plane wave solutions of the free equations of motion, those correspond to diagonalizing the translational symmetries, in other words, choosing additive characters. And those additive characters give rise to solutions to the equations of motion whose energy depends on the momentum as some power. Typically, it's the square in an ordinary field theory. But there's actually sort of a spectral parameter one could introduce in the p-adic case because one has to use the norm anyway. So the fact that the number that appears here in this free action that we wrote is 2 is kind of an essential. It could be 2 multiplied by some number or some shift of 2. It ends up being not so important. And I want to sort of maybe begin by circling back to something that I mentioned towards the beginning, I don't remember exactly when, which is that we have some new features in the p-adic setting. Namely, even though we have continuously many plane wave solutions, these are, of course, labeled by a momentum parameter, which is continuous. Uncountable, it's labeled by qp to the n dual, if you like. We have only discretely many energy levels. So countably many. And that basically corresponds to the fact that the p-adic norm is a discrete valuation. So it lands in a set of integer powers of p. And this sort of makes many things easier. That have to do with scale issues. And the renormalization group. So one example is that kinetic terms in p-adic theories are never renormalized. This is in strong contrast to what happens in the real case. So maybe let me, guess I'd like to say quickly what I mean by renormalization. And then I'll come back to the argument that kinetic terms are not renormalized. And then perhaps towards the end of the hour, I'll circle back to the idea of making the renormalization scale geometric. So coming back to the ideas about idiocy of T that I talked about at the beginning. So what is renormalization here? Let's imagine that I have some degree of freedom, which is a field. And perhaps it's defined on the p-adic unit ball, so ZP. And it lands in something like R. So we know that ZP is sort of naturally constructed as an inverse limit. It's the inverse limit of the quotients of Z by successive powers of the prime P. And so that means that we could think about a space of fields, we call this E. E is naturally a direct limit. And it's a sort of direct limit of the things I'll call En, where En is maps from Z mod P and C to R. And anything in En defines something in E because the p-adic integers map to this quotient. And so I can pull back a real valued function and view it as a function that's constant below a certain scale, locally constant at the scale defined by p to the n. And so En, if you like, consists of functions locally constant over distances, where the p-adic distance between x and y is less than p to the minus n. That's a way you can say it. Or you can say functions built from additive characters. So remember, there's Fourier theory 2 for ZP. And this is really saying that the size of the momentum should be less than or equal to p to the n. And if you think about it for a moment, you'll see that in the physics way of thinking about things, we often say, well, the story of the renormalization group is about sort of integrating out high momentum degrees of freedom or forgetting about short distance information. And in the p-adic case, there's actually a sort of filtration of the space of fields, which is a canonically defined filtration. It's a discrete filtration with integer steps. And at stage n in that filtration, we have precisely things which are exactly locally constant. The value is the same on any 2 points, which differ by a magnitude less than or equal to p to the minus n. And in fact, that precisely corresponds to functions whose Fourier decomposition doesn't include anything bigger than p to the n. So this is a sense in which things are actually cleaner in the p-adic setting than in the real setting. In the real case being bounded in Fourier space. Doesn't precisely correspond to being locally constant. Whereas here the intuition is exact. So how should renormalization work? Well, let's remember that I've got these maps. And correspondingly, on the space of fields, I've got a filtration going the other way. So here I've got En minus 1. En minus 1 sits inside of En. That sits inside of En plus 1. And these arrows are all restriction. But there's in fact something else I could do. I could construct a wrong way map. So I can do the following thing. I can take, let phi be an element of E. And I want to construct an element called R n phi, which will be an element of En. So you remember that En is actually a subspace of E. So the map goes the other way. We want to construct an averaging map by sort of integrating over the fiber. How do we do this? Well, the pre-image of x in Z mod p to the nz, it's a translate of p to the n times Cp sitting inside of Cp. And that's a compact subset. It has finite measure. So we can define Rn phi at x to be the integral over x plus p to the n Cp of phi of y dy. And we can normalize this appropriately by dividing out by the volume of p to the n Cp. I guess the volume of p to the n Cp, if I've normalized the measure appropriately, that'll be something like p to the minus n. So that should be something like p to the n. And this is just a map that literally averages the function phi over all of the points y, which correspond to a fixed point x. So in terms of the sort of hierarchical picture, people will have seen the tree description of the p-adic integers. So let me just draw it in the 2-adic case. And this continues on and so forth. Exponentially many things. And so the coordinate going down here is n. And if I think about the additive group structure at the first n levels, that's going to be a copy of the points of this layer will be in correspondence with z mod p to the nz. A function at that layer, which I can just think of as an assignment of real numbers to each of these points, that's going to be a field in En. The map from En to En plus 1 is the field that just says, at any descendant of one of those points, assign the same value to both points. That's pulling back along the quotient map. So let me think, I'll think about this as En plus 1. The map that goes this way, which is the canonical map, is pulling back, so just assigning the same value to both ancestors. The map that goes the other way, so the map that goes from En plus 1 to En, or in general from E to En, is averaging. And the map that goes the other direction is pullback. So what's the idea of renormalization? Well, suppose I have an action functional for fields on E sub n. Then I have this renormalization map, R, which carries the fields in En to En minus 1. This action functional is supposed to allow me to compute expectation values. For example, the partition function of this theory is going to be something like e to the minus s. When I write these brackets, what I mean is, yeah, maybe not, let me not write the brackets because I think that's confusing with the brackets I was using earlier. The idea is that I want to compute a path integral, and that path integral is going to be something like the integral over En of the expectation, the exponential of minus s of phi. So this is, in a sense, a path integral, but it's well defined because En is actually finite dimensional. And I want to think about defining the path integral over E, which is ultimately the sort of thing I'm interested in, as maybe a limit over a series of finite dimensional integrals, which I think of as being defined on the ENs. Now, what renormalization is supposed to do is it's supposed to give me a way of integrating out high momentum degrees of freedom. So that means that I've got this map R, which goes from En to En minus 1. And I'd like it to be true that the integral over En sorry, I will need to introduce some observables. So if I have some observable F, I could compute its expectation value. Which I'll define to be the integral over En of F times an expression of this type. So the idea of the renormalization group is that if F actually only depends that I can find some S prime So let's unpack a little bit what this says. It's saying that F is some observable. I could compute its expectation value using, so to speak, my ultraviolet degrees of freedom. All degrees of freedom up to a very high energy scale, N. Perhaps I have an R in the wrong place here. I think. Yeah, I think this R is in the wrong place. Sorry about that. So let me say in words what this equation is expressing. It's expressing the fact that if I have an observable defined at a low energy scale, so F is only independent on low energy modes. of my fields, then there should be a way of computing F by integrating only over low energy modes of fields with some effective action. That effective action is called S prime here. Of course, the way that the expectation value of F is actually defined, it says take F, view it as an observable on all fields. That's this pulling back along R. And when F is defined as an observable on all fields, then just compute the expectation value of that with respect to the ultraviolet action functional. That's what's happening on this side. So the idea of going from right to left is the idea of integrating out certain high energy modes. And the idea is that the effect of doing that, if the theory is renormalizable, should be able to be absorbed into an adjustment of the parameters that define the action. So that's a little bit of a mouthful. But the thing I want to emphasize is that in the p-adic setting, it's natural because the space E is already filtered. By the p-adic norm. Two, it doesn't break symmetries. So it's often a concern in the real world that when we go about introducing a hard momentum cutoff, that we often end up doing this in a way that sort of breaks symmetries, because it ends up being dependent on a frame. The p-adic world, it's sort of just a very natural thing to do. The condition that you don't depend on Fourier coefficients above a certain size just says that you're in a certain step of this filtration. And the last thing I'd like to say is that it's sort of inherently discrete. So the idea of integrating out one momentum shell is well defined. So at this point, I wanted to talk a little bit about some models in the physics literature where this renormalization group is sort of concretely worked out. I think in the interest of time, I probably won't say so much about this, but let me just give a few pointers to the literature. So models of this type are often called hierarchical. Models in the older physics literature. And there's quite a big literature about understanding renormalization from this perspective, which is really a sort of pleasant way of doing it. There are papers, for example, by Dorles, even by Wilson, in an early sort of block spin. Version of the renormalization group. And there are a great number of papers by Lerner and Misarov. Where there's an explicit connection to the p-adics. And maybe I'll just write down a result quickly. So it's from Dorles's paper, which I believe it's quite early. It must be, I think 1990 or something, 1990. And it's quite pleasant to see. I mean, the connection was not really made very explicit in this paper, but if you know about the p-adics and you go back and read it, it's sort of obvious that what's being studied is a field psi, which is in maps from the two adic numbers squared to fermionic, a real fermionic vector space, which I think in this case is actually pi r4. So this means 4 real fermions, 4 real fermionic degrees of freedom, per p-adic site. So this is clearly a model of the sort that we're talking about. And they study an action which is of the form sort of a standard kinetic term plus a mass term and finally a quartic coupling. And that quartic coupling looks like this. And this kinetic term is essentially the one from above. Or you can choose it to be this. And then the computation that takes place in this paper, they don't phrase it in this way, but there's a very explicit computation where you can consider fields which are in En, and you can consider pushing them forward via the renormalization map, this averaging map, to fields in En minus 1. And what they find is that S on En is equivalent to S prime on En minus 1, where S prime is of exactly the same form, but the parameters are related in a slightly strange way. So I'll just write the formulas for you. So the exact shape of these formulas is not that important to me. The thing that I want to emphasize is that these are really derived by integrating out exactly one momentum shell. And these formulas are exact. So that means that we have in this model, which is called the fermionic hierarchical models, gives a discrete, precise, concrete model, of renormalization group flow transformations. And the computations in most p-adic field theories are not that much harder than this. So the fact that it can be done exactly in the fermionic case, it roughly boils down to the fact that the manipulations are a little bit easier because the fermionic exponential function terminates. It's really just a polynomial. And so when you need to integrate out these high frequency degrees of freedom, you can do it by considering just finitely many terms. There's no sums to worry about. But in a typical p-adic field theory, the computations are going to be equally simple. And the analysis of the renormalization group effects, it's really going to reduce to some discrete action on the space of coupling constants. So like this, you can imagine that integrating out, going from En to En minus 1, that just generates a discrete transformation on the space of coupling constants R and G. And you could iterate that transformation to find a path in the coupling constant space. And you could look, for example, for fixed points of that path, which would be scale invariant p-adic theories. So p-adic analogs of conformal field theories, if you will. Okay, so I guess I have about 15 minutes. And I'm debating whether I would like to talk about non-renormalization for kinetic terms briefly, or whether I would like to try and say something about ADS CFT just very quickly. I think it's maybe of interest. It's maybe of interest to discuss this non-renormalization formula for kinetic terms. So. So given one of these p-adic field theories, it's actually possible to just think about analyzing it perturbatively in the same way that you would analyze any other field theory perturbatively. The way that you do this is that you take the quadratic part of the action, you diagonalize it in momentum space, the way we argued you could. And then you take higher order terms and you view them as defining vertices. So define vertices for Feynman graphs. For example, if I do phi to the 4 theory, then my action is the integral dx phi to the 4 of x. It's just the 4th power of x. And if I want to write this in momentum space, then it's integral dx integral dk1, dk2, dk3, dk4. There are 4 additive characters. And then there's 5k1. And then if I integrate out dx together with these characters, that's going to generate a delta function. So this will be the integral over all the k's, the product of all 4 of these phi's, and then a delta function which enforces momentum conservation. So that means that if I draw the corresponding vertex, in a Feynman graph, I'll assign it a weight that looks like just a delta function. Times some coupling constant. For example, if there was a coupling constant here, it would show up in front of that vertex. So normally the way corrections get generated is by diagrams of the following form. For example, here's a diagram I can build in phi to the 4 theory that would generate a correction to the propagator. So here I have a particle of momentum k. On the other side, I have another particle of momentum k. Here I have maybe some momenta L1, L2, L3. And I'm supposed to integrate over the loop momenta here. The loop momenta are in the high momentum shell. So I'm imagining if I do a renormalization type computation, the way I did up here, the way I do that is by separating out the degrees of freedom in the field psi into sort of low momentum pieces, which I view as physical and keep around, and high momentum pieces, which I integrate out. And it's the high momentum pieces that generate the corrections here that change my effective values of the coupling constants R and G. And if I had wanted to, or if I had had time, we could have set up this story about the hierarchical model, which is pretty simple to do by hand, in terms of Feynman graphs, where exactly those degrees of freedom run around in loops. So the kinds of diagrams that are going to cause problems for me are the ones where the internal degrees of freedom are ones that are integrated out, but the external degree of freedom is physical. So if all of the degrees of freedom were just physical, low energy degrees of freedom, that would just be incorporated by taking the same proportionality constant in front of the same vertex. But this, because the red lines are now no longer degrees of freedom that are around in my theory, they're too high energy, I need to sort of absorb this into a shift of the propagator, a shift of the effective coupling constants in the quadratic part of the action. And normally that can change both the kinetic term and the mass term. But in this case, it actually can't. And the reason is the following. So value proportional to I'm integrating over just high energy degrees of freedom. And then I've got a delta function that enforces momentum conservation. Times whatever else the integrand is. That'll be some functions of the degrees of freedom. And the point is that this actually can't depend on K. Just from the form of the integral, I can see that there's no way for a non-trivial K dependence to appear here. And the reason is because of the ultra triangle inequality. So the ultra triangle inequality means that if I just absorb the shift by K into, for example, L3, the norm of L3 minus K is exactly the same as the norm of L3, because by assumption, K was smaller, right? K was a physical field. And furthermore, the map that sends L3 to L3 plus K is just an automorphism of the momentum shell. And so in that sense, you can imagine that the errors that would occur, that it's the K dependence of this integral that really causes you problems in the ordinary case. And that leads to a non-trivial renormalization of the kinetic term in the action. For the types of kinetic terms that occur in p-adic theories, precisely because of the ultra triangle inequality, the K-dependent piece of this integral is actually literally zero. And it really just reduces to this fact. So.
Sorry, Idmar, you have 5 minutes.
Yeah, I think in fact I'm going to wrap up right now. I don't know that there's much time to go into ADS-CFT. So maybe I'll just give a couple of small words of summary. I think the main thing that I wanted to get across, this was a bit rushed at the end, but the main thing that one should hopefully take away from it is that in the p-adic case, it's possible to set up a lot of field theories in this example 2 that we're talking about. So where we take the space of parameters to be p-adic, many things work exactly the same way as they would in the real case. But some things even work better. The things that work better tend to have to do with scale transformations. And from my perspective, it's precisely because the valuation on the p-adics is a discrete valuation, and the norm is actually ultrametric, so it satisfies the ultra-triangle inequality rather than just the standard triangle inequality. That means that several unfortunate features in the real case are sort of erased, or several approximate intuitive pictures that you have in the real case are literally true in the p-adic case. So that's a sense in which the class of models 2 is a class that really contains a lot of physically interesting and kind of richly structured phenomena. And I've run out of time to tell you anything more about it, but I don't know. I hope that this was of use. I hope that people learned something from it. And I'd like to thank Wilson for the invitation to give these lectures, and I'd like to thank all of you for your attention. It's really been a pleasure to be with you.
Thank you. Are there comments or questions? Okay, I have a couple of comments, Igmar. First of all, in general, p-adic quantum field theories require renormalization. It happens that the example that you presented is quite particular. You presented an example of a one-dimensional theory with a parameter equals 2. Mm-hmm. If you change this parameter 2 by beta, and beta is between 0 and the dimension, then the green function has singularities. If beta is greater or equal, is greater than 1, the green function associated with the theory is a continuous function. You see?
Mm-hmm.
So in general, the p-adic quantum field theories require renormalization.
They certainly require renormalization. I think my claim is that the momentum-dependent thing does not require renormalization. So there's no field strength renormalization. There will certainly... There's no...
I didn't get that part.
So it's... The statement is not that there's no renormalization. Certainly there is.
Okay.
The statement is that there's no momentum-dependent renormalization. I think people sometimes talk about this as, they would call it field strength renormalization.
Okay, now it's terminology. Okay.
Yeah.
Okay, I got it.
Even in this example here, right, where this is some two-adic field theory in a sense. This is saying that there's some very non-trivial renormalization of the coupling constants R and G. It's the kinetic, yeah.
No. Probably, I'm going to send you an email later about it. Let me tell you something that recently I published an article in Reducing Mathematical Physics where I presented a mathematical rigorous theory of Euclidean quantum fields. Okay. Mm-hmm. And another observation: there is a paper by Abdel Salah and his collaborators where they provide a rigorous mathematical construction of the renormalization theory in the p-adic framework. This is a very long paper available in the archives.
Mm-hmm. Mm-hmm.
Are there more questions or comments? Okay. Oops.
Thank you. I think you mentioned it very briefly, but I have a question. In this renormalization group, though, do we have fixed points, which would be analogous to the conformal field series? And
yeah, so
explicit Lagrangian actions for them.
So in general, there will be fixed points. Yeah. So in the hierarchical model, there are two. I believe in this case, they look like. Let's see, one of them is like, of course, the free theory, but I think there's a non-trivial one, and it looks maybe something like, Oh, did I write it somewhere? It's a pair of numbers. Yeah, here we go. RG, yes. -4/3, 8/27. So in a sense, there is an interesting interacting fixed point of the renormalization group flow here. It's this one. And that's going to be some scale invariant theory.
Thank you.
Thank you very much.
Okay, let's thank the speaker again. Thank you very much, Igmar, for this very appealing course.
Thank you so much. Thanks to everybody for being here.
Now we have a conference by Professor Ultrametric. Let me see if this guy is around. Oh, hello, Kodor. Can you hear me?
Yes, hi, Wilson.
Okay, we are ready for your talk.
Okay.
So
maybe if Ingmar stops sharing, yeah.
perfect.
Okay.
Do you want to share your screen?
Yeah, that's what I'm doing. Can you see it?
Yes.
Okay.
Yeah. Okay, let me see. Okay.
All right. So,
Give me a minute. Okay, it is a pleasure to announce the closing lecture by Professor Kodor Chancery. The conference of Professor Chancery was scheduled for May 23rd, but unfortunately there was a blackout in Guanajuato, and we lost the access to the internet. For this reason, we rescheduled the talk of Professor Chancery. So Professor Chancery is going to talk about non-Archimedean valued fields, ultrametric spaces, the Ham fields, and the Levi-Civita fields. Welcome.
okay. So first, I would like to thank the organizers, especially Wilson, for the opportunity to speak to you today. So my talk is a survey of non-Archimedean valued fields and ultrametric spaces leading to the Hahn fields and Levi-Civita fields, which are non-Archimedean valued fields different from the p-adic fields, which have been the focus of this research school. So I will tell you what's special about these fields in this talk. So here is the plan for my talk. First, I will give a review of non-Archimedean valued fields and ultrametric spaces, showing you the close connection between these two mathematical objects. Then I will give some examples of non-Archimedean valued fields. And I will end with a summary of my work and my research group on two very special Levi-Civita fields, and I will tell you what's unique about these two. So let me start by talking about non-Archimedean valued fields by first introducing what we mean by evaluation on a field. Evaluation on a field K is a map from K to the set of non-negative real numbers that satisfies these properties. And a close look at these shows that the valuation is a generalization of the concept of absolute value on R and C. The pair K valuation is called a valued field, but for simplicity, we will sometimes denote it by K. The set of all valuations of non-zero elements of the field is called the value group, and it is isomorphic to a subgroup of the multiplicative group of positive real numbers. We say that the field is non-Archimedean, or that the valuation is non-Archimedean, if the following set, which is obtained by adding the neutral element for multiplication of the field to itself multiple times, is bounded with respect to the valuation. So we can think of this set as a copy of the set of natural numbers in the field. Otherwise, we say that the field is Archimedean. Of course, in R and C, N is unbounded with respect to the usual absolute value. So R and C are Archimedean. Some of you have seen probably other definitions of non-Archimedean valued fields. So in the following theorem, I will state other equivalent conditions. So the field is non-Archimedean in this sense, if and only if the valuation satisfies the strong triangle inequality. So this is stronger than the usual triangle inequality, where we have the valuation of A plus B is less than or equal to the sum of the two. If and only if the valuation of A plus B is equal to the maximum whenever the two valuations are different, if and only if the valuation of n times 1 is less than or equal to 1 for all n in n. So while this, in appearance, this last condition is stronger than the original definition, in fact, they are equivalent. Okay. Then we define what we mean by ultrametric spaces by first recalling what we mean by a metric on a set. A metric on X is a map from X cross X to the set of non-negative real numbers that satisfies these three conditions, which are also reminiscent of the properties of the distance in Euclidean spaces. The pair X delta is called a metric space, and again, for simplicity, sometimes we just write X. Now, given a metric space X, a point A in X and a positive real number, we can define the closed and open balls like we do in Euclidean spaces. And then we use the open balls to define a topology on the space. We say that a subset is open if for every point in the set, we can find a whole open ball centered at that point contained in the set. And the collection of all open sets forms a topology on X, which is called the topology induced by the metric. Okay, so this is for any metric. Now, when do we call the metric an ultrametric and the space an ultrametric space? When the metric satisfies the strong triangle inequality. Okay, instead of having a plus here, we have the maximum of the two. And like we showed with the valuation, it turns out that this condition is equivalent to saying that this is equal to the maximum whenever these two are different. And this is stated in the following theorem, which is known as the isosceles triangular principle, Why? Because if we think of x, y, z as the vertices of a triangle in this ultrametric space, then either xy, the length of this side, is equal to the length of this side, yz. Otherwise, xz, the length of this side, will be equal to the maximum of the two. So for any triangle, at least two sides will have the same length. So all triangles are isosceles. Okay, and now we come to the connection between non-Archimedean valued fields and ultrametric spaces. First, I note that whenever you have evaluation on a field, we can use that to introduce a metric, to define a metric as follows. We define a delta of AB to be the valuation of A minus B. And it's easy to show that this will be a metric, and therefore it will introduce a topology on the field and turn it into a topological field. Then we say that the valued field is complete if it's complete with respect to this metric. So any Cauchy sequence with respect to this metric will converge. Okay. And it's a known fact that if K is Archimedean and complete, then it's topologically isomorphic to R and C. So R and C are the only Archimedean complete fields. Therefore, almost all complete valued fields are non-Archimedean. So they are worthwhile studying. All but two of the complete valued fields are non-Archimedean. And we can see from here that if the valuation is non-Archimedean, which means it satisfies the strong triangle inequality, then the metric that we obtain this way will also satisfy the strong triangle inequality, and the metric becomes an ultrametric. So every non-Archimedean valued field is an ultrametric space. And in fact, we obtain this way all examples of ultrametric spaces because each ultrametric space can isometrically be embedded into a non-Archimedean valued field. Okay, so every non-Archimedean valued field is an ultrametric space, and every ultrametric space can be embedded in a non-Archimedean valued field. We may not have the field structure to say we have a one-to-one correspondence between the two. Okay. And now I will state some of the counterintuitive or unusual properties of ultrametric spaces. Some of these were covered by Trond on the first day, in the first mini course, with proofs in the context of the p-adic field. So here I will state this in general for any ultrametric space, and it's not surprising that they hold in the same way because they are a result of the strong triangular inequality of the ultrametric. So they work here in the general context for the same reason they work in the p-adic context. So let X be an ultrametric space, then each point of a ball can serve as the center of the ball. So you can shift the center from A to any point of the ball, and the new ball will be equal to the old ball. Each ball is both open and closed, which means Kloppen, and has an empty boundary. I believe Wilson showed that in the p-adic context. Two balls can either be disjoint or one contained in the other. They cannot have a proper overlap. Moreover, if the two balls are disjoint, then the distance between them, which is by definition the infimum of all distances between one point in B1 and one point in B2, can be evaluated by measuring the distance between an arbitrary point in B1 and arbitrary point in B2. What does that mean? It doesn't matter what point in B1 you choose, what point in B2 you choose, you get always the same distance. So this set here, over which we're taking the infimum, has only one value. Okay, so this looks counterintuitive to what we are used to in the classical case. The topology induced by the metric is zero-dimensional, which means there is a base of the topology consisting of Kloppel sets. And that entails that the space is totally disconnected. So that leads to difficulties when we try to do analysis in the non-Archimedean setting. And we have this nice result that if we have a sequence in an ultrametric space, then this sequence is Cauchy if and only if the limit of the distance between two consecutive terms goes to 0. And as a corollary to this, we obtain this result, which is every undergraduate student stream. Also, this was mentioned by Trond in the on the first day, that if we have a complete ultrametric space or non-Archimedean valued field, and AN is a sequence in K, then this sum converges if and only if the nth term goes to 0. In the classical case, of course, one direction is true, but not the opposite one. Okay. It turns out that in the non-Archimedean setting, there is a new notion of completeness that is more useful than a Cauchy completeness or sequential completeness. And this is called spherical completeness. So an ultrametric space is called spherically complete if each nested sequence of balls has a non-empty intersection. And it turns out that this is needed. This concept of spherical completeness is needed to make the Hahn-Banach theorem work in the ultrametric setting. So the Hahn-Banach theorem works if and only if the ultrametric space is spherically complete. And by looking closely at this definition, you can see that spherical completeness implies Cauchy completeness, but the converse is not always true. And I will give you examples at the end of the talk of non-Archimedean valued fields that are Cauchy complete, but not spherically complete. Okay. And besides the Hahn-Banach theorem, there are two other attributes of spherically complete ultrametric spaces. The first one is the following. We obtain a stronger version of the fixed point theorem. So in this setting, if we have a spherically complete ultrametric space, then every shrinking map, we don't need a contracting map to get a unique fixed point. Okay, so it's enough that the distance between f of x and f of y be less than the distance between x and y to get the fixed points here. We don't need a contraction factor less than 1. So this is one nice thing we get out of spherical completeness. Another attribute is the existence of best approximations. So if we have a non-empty spherically complete ultrametric space Y embedded in another ultrametric space X, then each X in X has the best approximation in Y, which means this minimum of all distances from X to a point in Y exists. Okay. For non-spherically complete ultrametric spaces, this doesn't exist. And I should mention here that best approximations need not be unique. So one point could have infinitely many such Y's satisfying the minimum. Okay. Before I do some examples, any questions at this point?
No, at the moment there are no questions.
Okay. So now I will give some examples of non-Archimedean valued fields. As I mentioned, since p-adics were discussed in details in the mini courses and the other talks, I will skip these two slides to gain some time. So I will talk now about ordered fields. Let K be an ordered field. We can introduce a relation between non-zero elements of K. We say that non-zero X and Y are comparable, and we write X tilde Y if there exist natural numbers M and N such that NY0 exceeds X0 and MX0 exceeds Y0, where A0 is the ordinary absolute value defined to be A when A is non-negative and minus A if A is negative. And this relation is an equivalent relation on K star. The equivalence class of X will be denoted with square brackets, and the set of all equivalence classes, also known as Archimedean classes, is denoted by GK. It turns out that GK is an ordered abelian group under the following order relation and addition, which are defined as follows. We say that the class of X is less than the class of Y if NY0 is less than X0 for all N. And in this case, we say that Y is infinitely smaller than X. And we define the addition of the classes as the class of the multiplication. The neutral element with respect to this addition is the class of 1K, where 1K is the multiplicative and neutral element of the field K. And the additive inverse of the class of X is the class of X inverse for any X in K star. Okay. And now, with respect to the order, we say that the field is Archimedean if GK contains only one element, namely the class of 1K. And that means that all non-zero elements of the field are comparable. Okay, that's the case, of course, for R. All non-zero elements of R are comparable. And not only is R Archimedean with respect to the order, each Archimedean ordered field can be embedded in R. So in that sense, R is a maximal Archimedean ordered field. Now, Hans Hahn in 1907 generalized this property of R, and he ended up with ordered fields that, like R, extended all ordered fields with a given level of non-Archimedicity. And I will explain what I mean by that. Okay. So let E be an order field extension of K. Then we say that E is an Archimedean extension of K if every element of E is comparable to some element of K. Okay. In this case, the two groups GE and GK, these are the sets of Archimedean classes under the order relation that we introduced. These two groups are isomorphic ordered groups. We say that an ordered field K is Archimedean complete if it has no proper Archimedean extension fields. Okay. Like R. R is Archimedean complete because we cannot extend it to with an Archimedean extension. And now I introduce another definition. Given an ordered field K, if G is an ordered abelian group that is isomorphic to GK, which is a group of Archimedean classes, then we say that K is of type G, and that G is an Archimedean group of K. So this will be useful later when we introduce the Hahn fields. As I mentioned, R is Archimedean complete with respect to the order. It is the simplest Archimedean complete field because the smallest G contains one element, and R is up to an isomorphism, the only Archimedean complete of type 0. Archimedean complete fields of other types, G, are given by the general Hahn fields, which I will talk about next. Okay, so I will show that the general Hahn fields that I will introduce next play the same roles in the non-Archimedean case of ordered fields that R plays in the Archimedean setting. So given any field, not necessarily ordered, and an ordered abelian group G, we define K of G to be the set of all maps from G to K with well-ordered support, where the support is the set of all points where the function is not 0. Okay. So these are the all maps with well-ordered supports. That means any non-empty subsets has a lowest point or a minimum. Then it turns out that K of G is a field under addition and multiplication defined this way. Addition component-wise and multiplication as a convolution. Fields of this form are called general Hahn fields. Now, I said here K does not need to be ordered. If it is ordered, we can then introduce an order on the general Hahn field as follows. First, we define lambda of F for non-zero elements of this field to be the minimum of the support, which exists because the support is well ordered. Okay, and the support is non-empty, so it has a lowest point, the minimum. Now, for two elements of the field, we say F is less than G if F is not equal to G. and f minus g as the lowest support point is negative. So we look at f and g. If they are different, we look at the first point where they are different. If f is smaller than g at that lowest support point, then we say that f is less than g. So we can think of this order as a lexicographic order going from left to right. Then this field with the order relation less than or equal becomes a totally ordered field. Okay, but now I'm ready to state the two key results about general Hahn fields as ordered fields that mimic what happens in the Archimedean case for the real numbers. Okay, so the first one is the Hahn's embedding theorem, which states the following. Basically, what this says, if K is an ordered field of type G, where G is an ordered abelian group, then K can be embedded into R of G, which is the general Hahn field R of G, such that R of G is an Archimedean extension of the image of K. So this is similar to saying every ordered Archimedean field can be embedded in R. Okay. And the other result has to do with the maximality. Hahn's Completeness Theorem says for any ordered abelian group G, the general Hahn field R of G is up to an isomorphism the only Archimedean complete ordered field of type G, like R is the only Archimedean complete ordered field of type 0. Okay. So the general Hahn fields as ordered fields play the same role in the non-Archimedean setting as the real numbers do in the Archimedean setting. Okay. All right. So far, G was an arbitrary ordered abelian group. Now, if we take G to be a subgroup of R plus, then we call the general Hahn field simply a Hahn field. Okay. So a Hahn field is a general Hahn field for which G is a subgroup of R plus. And when this is the case, we can introduce a non-Archimedean valuation on the Hahn field K of G as follows. The valuation of F is E minus lambda of F when F is not 0. Remember, lambda of F is the minimum of the support. So it's in G, and G is a subgroup of R. So this is a real number. So this makes perfect sense. With respect to this valuation, the Hahn field is a spherically complete non-Archimedean valued field with value group of the form E.g. G in G. Okay, and now we can introduce the Levi-Civita fields as subfields of the Hahn fields as follows by requiring the support of the maps from G to K to be left finite instead of well ordered. By left finite, I mean below any integer, there are finitely many elements of the support below n. Okay. Of course, every left finite set is well ordered. So this is a subset of the Hahn field. And with the addition and multiplication, it becomes a subfield of the Hahn field. So let's look what happens, because the support is left finite. So we can, using induction on the positive end, we can arrange the elements of the support in ascending order. This is lambda, G1 is equal lambda of F. And then what will happen? Either this sequence will terminate at some point, so it will be a finite support, or if it's infinite, it has to diverge to infinity. We cannot have infinitely many support points that are bounded from above, because this will violate the left finiteness of the support. Fields of this form are called Levi-Civita fields. And now if we restrict the valuation that we defined on the previous slide on the Hahn field to this subfield, the Levi-Civita field becomes, with respect to this valuation, a Cauchy-complete non-Archimedean value field with value group the same as that of the Hahn field. Okay, so here we get Cauchy-complete, but not necessarily spherically complete. Okay. Now, given any field K, and this map D from Q to K defined as follows: D of X equal 1 when X is equal to 1 and 0 otherwise. So this map has only one supported point. So the support is less finite. So this is an element of the Levi-Civita field L of QK. Moreover, for any R in Q, dr exists as an element of the Levi-Civita field, and it's given by this map, dr of X equal 1 when X equal R and 0 otherwise. So again, for any R, dr has only one supported point at X equal R. And this number D, which is an element of the Levi-Civita field, serves as a generator of all the elements, in the sense that every non-zero element of the Levi-Civita field can be written in this form as a generalized power series, where the exponents of D are the elements of the support, and the coefficients are the function values. And this converges in the valuation topology, or with respect to the ultrametric that we obtained from the valuation. And how do we see that this always converges? Remember, we said the support of F is either finite, or if it's infinite, the sequence of the support points has to diverge to infinity. So let's assume there are infinitely many points in the support. So R will have to go to infinity. So dr will have to converge to 0, because the valuation of dr will be e to the power minus r. So if r goes to infinity, this goes to 0, and the valuation of f of r dr, because this is a real number, is e minus r, so it goes to 0. Because the nth term goes to 0, the whole thing converges. So it's nice that any non-zero element can be written as a generalized power series. Okay. The following result tells us exactly when the Levi-Civita field, this one and this one, are coincide. So this will be equal to the larger field K of G. So given any field K and G a subgroup of R plus, then the Hahn field K of G and the Levi-Civita L of GK coincide if and only if G is discrete, if and only if L of GK is spherically complete itself. Okay. So what does that mean? If G is not discrete, then this will not be spherically complete. And we saw that this is always Cauchy complete with respect to the evaluation. So we have many examples of non-Archimedean valued fields that are Cauchy complete, but not spherically complete. Now, if K happens to be ordered, remember, then we can define an order on the Hahn field, which is the same as the order on the subfield, the Levi-Civita field. And in this case, the Hahn field is an Archimedean extension of the Levi-Civita field, L of GK, which means every element here is comparable to some element in this smaller field. Moreover, if K is Archimedean as an ordered field, then both of these fields are of type G. Okay. Now, we said if K is not ordered, the general Hahn field K of G need not be ordered, but some general Hahn fields are real closed. And the following result tells us exactly when this happens. So the general Hahn field K of G is real closed if and only if K itself is real closed and G is divisible. Okay. So what we mean by real closed is that all positive all elements have roots of order n. Like if n is odd, all elements have nth roots, and any polynomial of odd degree has at least one root. If we take the Levi-Civita field L of QK, then this is real closed if and only if K itself is real closed. And from these two results, we obtain that the Hahn field R of Q and the Levi-Civita field L of QR are real closed. Okay. That this is real closed we obtain from here, and this we obtain from here. And this entails that the complex versions of these, namely the Hahn field C of Q and the Levi-Civita field L of QC are algebraically closed. Okay, it is these special non-Archimedean fields, the Levi-Civita field L of QR and L of QC, that are unique among all non-Archimedean valued fields, and I will tell you soon how they are unique, and that's why they have been the focus of the work in my research group. So I denote L of QR by R script and L of QC by C script. So R script is the set of all maps from Q to R with left finite support, and C script is the field of the maps from Q to C with left finite support. So what's unique about these two fields? They are unique from a pure mathematical point of view and from a computational point of view. In fact, R script is the smallest Cauchy complete and real closed non-Archimedean field extension of R. Okay, it is small enough that we can implement the numbers on the computer because the support of the elements are left finite. We can cut the implementation of the numbers up to a certain power of d and use the numbers for computational applications. One such application that I did a long time ago as a student was the computation of derivatives of real valued functions, any function we can type on a computer. And the result was that we get derivatives whenever they existed with the accuracy of Mathematica and with the speed of classical and numerical methods. So the best of both worlds. C script, on the other hand, is the smallest Cauchy complete and algebraically closed non-Archimedean field extension of C. So here I will list some of the research topics that we did on the Levi-Civita fields R script and C script. We studied the topological structure in the natural topology, the valuation topology, and in another weaker topology that comes from a countable family of seminorms. We needed this weaker topology to be able to extend converging real and complex power series to the new fields, since those do not converge in the valuation topology. And then we studied power series and analytic functions under the weak topology, and we showed that these behave as nicely as real and complex power series. We succeeded in extending all the fundamental theorems of real calculus, like the intermediate value theorem, mean value theorem, extreme value theorem, inverse function theorem, under very mild conditions. We did Lebesgue-like measure and integration theory on R script 2, R script 3. We did optimization, operator theory, and some computational applications. If you are interested to learn more about the Levi-Civita fields, there are many papers here about individual research topics. In addition, you can find the survey paper based on which I did this talk on non-Archimedean valued fields in general. And with this, I thank you for your attention.
Thank you very much. Let's thank to the speaker. Are there comments or questions? Okay, let's thank the speaker again.
Thank you.
Thank you, Godot. We had reached the end of the conference. I want to take this opportunity to thank all the speakers for participating in the conference. Also, I want to thank to Cimpa and CIMAT for supporting the conference. To the audience, thanks for coming to Guanajuato. I hope that we can meet somewhere in the near future. Now, Tron want to say some words.
Thank you, Wilson. So as one of the two scientific coordinators, I would also like to thank the local organizing committee and to Wilson also, and I would also like to thank all the speakers. And in this context, I represent Norway, which is one of the 4 nations which sponsors Cimpa. There is Norway, France, Switzerland, and Spain. And as a representative for Norway, I'm very pleased to see how well this conference came around. And also I have to say it was fascinating to witness the talks, which shows, shows that the non-Archimedean methods are finding their way into an ever-expanding catalog of applications. That's really fascinating to see. And with that, yeah. So I just, will sign off by once again thanking the local organizers and the speakers. Thank you very much.
Thank you, Tron. Does somebody in the audience want to say something? Okay, guys. Bye-bye. Bye-bye.
Bye.
Bye-bye, Eddie. Now it's no time. Yo soy de la ciudad. Sí, se puede hacer.